Hi guys, Buildzoid here, and today we're going to be taking a look at that GTX 780 Ti DirectCU2 PCB that I resurrected. So yeah, this is the card. There's not actually that much on it compared to some of the other NVIDIA cards. Like this really isn't that complicated. So let's get right into it. This down here is the 1 volt PEX VRM, or it might be 0.95. I'm not entirely sure, but yeah, so that's the PEX/PLL. It helps to tweak this up a bit on liquid nitrogen, but other than that, it's not really that important. Well, actually, even on air and water, it can help to tweak this up a bit to improve overclocking. I can't get any information on that. Then the main VRM and the one that didn't work when I first got the card is this right here, which is the V-Core VRM. So yeah, and the problem with that was that basically that V-Core VRM uses this, give me a second, it uses this chip this LDO right here, and that puts out 5 volts, and that 5 volts is necessary for these chips to work, and without those, the V-Core VRM won't turn on. So yeah, that was the malfunction, the main malfunction on the card when I got it. But that's the V-Core VRM. Above that, you have the memory VRM, so that's VMem up here. And that powers all the GDDR5 memory chips, which there is 3 gigabytes of memory on this. This is a 780 Ti. So, yeah. The V-Core VRM is a 1, 2, 3, 4, 5, 6, 7, 8 phase. This is a true 8 phase. The chip right here controlling it is a ASP 1212. I actually misspoke in the video where I talked about finishing off the repairs on this card. It's not an ASP 1211. That's on the HD 7970 DirectCU2 I recently got. That's where the mistake came from. It's an ASP 1212. This has a public product brief. So it's basically like it's the first 3 pages of the data sheet. It includes a typical application diagram as well as the pinout and some feature specifications. And this is an 8-phase controller from Infineon, actually International Rectifier, so IR. But it doesn't have the IR part number because this is relabeled to be a DigiPlus VRM component for ASUS. I'm not sure, I didn't bother to write down the switching frequency ranges on this, but if I remember correctly, it's 200 kilohertz to like 2 megahertz, just because that's a really common range for most international rectifier voltage controllers. This thing uses a parallel vid interface, so PVID. That is it uses, a parallel vid interface, and basically that's located along this edge of the controller, which is why we have this sort of resistor network right here. I'm going to try fiddle with this for voltage control because I've never actually worked with a voltage controller that uses PVID before, and it could be an interesting way to change voltages instead of just doing the usual feedback pin mod. Instead of just modifying the feedback circuit, this could be more interesting as well as potentially more reliable, less fiddly to set up. So yeah, and I want to mess with that, but the only issue I can think of with doing that is that if I'm not mistaken, the PVID maxes out at I think it's 1.55 volts or something like that. It doesn't go super high voltage. So yeah, that's a thing. And then this group of capacitors and resistors around the card, around the voltage controller, that's the current sense for each and every phase. So you have 1, 2, 3, 4, 5, 6, 7, 8 current sense. Think you'd call this a filter. Either way, that's the circuitry that is used to basically convert that the voltage controller uses to scale the what does it do? Either way, like this stuff is used for current sensing. I'm not gonna explain specifically how it works because I don't really remember. What I do know, though, is if you tweak the resistance from one side of each of these, like if you put a capacitor in parallel with these resistors, you can scale the you can scale the current reading up and down, because basically the way this works is it uses through some complicated math and this lovely circuit right here, it's capable of basically figuring out the current going through an inductor based on the direct current resistance of the inductor. Now, obviously, the current through an inductor and the voltage across the inductor isn't constant, so that's why you have all of this circuitry right here. But basically, if you put a resistor in parallel with that capacitor, what you're going to do is you're going to scale down the voltage difference across that capacitor, and that makes the current reading lower. So that's one way to potentially remove things like overcurrent protection if the card trips it, which it might, because this VCore VRM is not exactly spectacular. This is like one of the phases. Each phase is controlled by, each two phases, so like these two, are actually controlled by this chip right here. And that is the IR3598. And so that is a dual driver. So there's two PWM signals from the voltage controller, which that's not, like, those lines aren't to the correct side. I'm actually not sure where they're supposed to go. But you're going to have two PWM lines going from the voltage controller to one of these chips, and that's going to then spit out a drive signal for each phase. Well, drive signals for each phase. So, yeah, the 3598 can also work in a doubling mode where you put one PWM signal in and get two phases out, and it interleaves them. So, yeah. But this is a true 8-phase even when you have only like 4 drive chips like that, because they are dual drivers. Now, each actual phase is made up of a high side MOSFET and 2 low side MOSFETs. So the high side MOSFETs is the ASUS favorite UBIC semiconductor, which UBIC semiconductor is like partially owned by ASUS or something like that. They're part of the ASUS like group, whatever that is. So ASUS really likes using these MOSFETs a lot. Like, they're really common, especially on their GPUs. And this one right here is a QM3054. And it's not particularly great. It's kind of slow. And then the low side MOSFETs are also UBIC semiconductor, but these are QM3056s. And those are... Wait, did I get that right? Yeah, I did get that right. Those are even worse. So, in terms of a low side MOSFET, these are 4.2 milliohms per. They're 4.2 milliohms RDS on, which basically means that each of these phases has like 2.1 milliohms of RDS on the low side, which is kind of awful. It's really like really high end cards, like say. If you compared this VRM like to the VRM on the GTX 780 Ti classified that I have from the guy who sent in this card sent in the classified as well. The classified has a low side MOSFET which is like 1.7 milliohms RDS on, and that's a 14 phase. So that thing has a low side RDS on that's like less than half of what this has, like a lot less than half of what this has. So this VRM right here is not particularly efficient, and it's actually kind of concerning for when I want to put the card on liquid nitrogen. I'm kind of worried it'll catch fire. So I've repaired the card, and I'll probably kill it again. Assuming this doesn't trip over current protection. If it does trip over current protection, then I'm going to probably end up modifying the current sense circuitry to basically lift the current limit, because, I don't know what register on the ASP1212 is the overcurrent protection programming, or even like some international rectifier chips have a register which you can set it to ignore all safeties, which is kind of fun. But I don't know which register it is on this chip specifically, so not particularly helpful. Anyway, let's talk current output capabilities. So pushing pushing current into the GPU core. For these calculations, I'm assuming that the VRM is running at 200 kilohertz, not 300 kilohertz like usual, because these inductors are actually very high inductance. They're like 350 nanohenry, which is Well, normally most cards would be like 220 or around that 200 nanohenry figure, but these are 350, which is pretty damn high for a V-Core VRM section. So I'm assuming that's to lower the switching frequency, which does improve the VRM's efficiency quite a bit. The drive voltage on this thing is a 12-volt gate to source. The MOSFETs are literally just driven off of straight 12 volts. So, yeah, that's what I'm working with in terms of the MOSFET operating parameters. The end result is that for stock settings, where you'd be looking at something like 1.17 volts, 200 amps, 780 Ti's are not. 780 Ti's are actually really power hungry. I don't know how a lot of people seem to not remember that these things easily have like 200, like these are almost as bad as 290X's at stock. And if you overclock 780 Ti's, they actually get a hell of a lot worse than a 290X, as you'll soon see. So yeah, 1.17 volts, 200 amps into the core, and you're going to be looking at about 30 watts of heat output on the VRM. So that's hot. Like, that's really not great. For high-end GPUs, around 200 amps output, I'd be looking around around 15 to 25 watts of heat output. 15 is like super high-end 16-phase monster VRM. 20 watts is like that's not exactly hard to hit for this current output with the right components. 30 is very much on the sort of miserable end of things, but that 30 watts is spread across quite a lot of surface area, because you got to understand, like, if these were power stages, not discrete MOSFETs, a power stage like takes up like this much space, right? So these are like the thermal density of this VRM is relatively low, but it's not efficient. So it shouldn't necessarily overheat, but it's not an efficient VRM, that's for sure. Now, for 1200 megahertz, which I'm not sure when a 780 Ti will hit 1200, but I'm assuming it should be around 1.25 volts, you'd be looking at about 240 amps output and about 40 watts of heat from the VRM. Same thing. Like this is not a great efficiency, but with how large the VRM is, it shouldn't be too much of a problem, I'm hoping. 1300 megahertz, I'm assuming you'd hit at around 1.35 volts, and I forgot the V's. For that, you'd be looking at about 280 amps of current output and about 52 watts of heat. That's gonna get toasty. And then for 1400 megahertz, which 780 Ti's can hit on water cooling for benchmarks, 1.45 volts, it's about 320 amps output and about 65 watts of VRM heat. That is concerning, to say the least. That's hot. This is really hot. It should still be coolable. If you throw a big enough fan on it with high enough airflow, and I'm actually going to be mounting I have a VRM heatsink that does fit this, that comes off of a motherboard, which is like massive. Oh, like it's a huge heatsink. Well, you've seen it on the 7950, I think, in some pictures. I'm not sure. Either way, I do have a motherboard heatsink that'll fit onto this VRM just fine and cover all the MOSFETs, so that's what I'll be running it with. And, well, given enough airflow, that should be able to handle 65 watts of heat, but yeah, this is going to run hot. And then once you go on liquid nitrogen, now I'm not scaling this for the temperature, the current, I'm not scaling it properly. 1850 megahertz, I'm not sure if the card will actually hit that. 780 Ti's are kind of a problem because, like, there's scores from Kingpin with the card doing apparently over 2 gigahertz, and then there's everybody else around 1800. So yeah, I don't know what the hell is up with that, but nonetheless, 1850, 1.7 volts, you'd be looking at 500 amps if the card didn't get colder. The problem is your power consumption actually gets better as silicon gets colder, because there's less leakage. There's also less electrical resistance in the internal copper wiring. So, everything runs more, it'll run more efficient if you get it really, really cold. So on liquid nitrogen, and this calculation is done assuming like 70 degrees centigrade, Celsius, core temperature. So yeah, this current figure might be too high. It might be more like 400 amps on liquid nitrogen, but nonetheless, that's a lot of current. And the end result is, even at 400 amps, it would still be a lot of current. And the end result is that this VRM will produce about 148 watts of heat for that 500 amp 1.7 volts figure. At which point, the VRM also has to stay under 135 Celsius, because if it goes, degrees Celsius, if it goes over that, either the high side or the low side is blowing up. They're actually really well, at that 200 kilohertz switching frequency, the high side and low side are really well matched in terms of when each reaches its current limit. So, yeah, if this goes over 135, it's going, yeah, high side or low side MOSFET is blowing up. If the switching frequency is higher, then the high side MOSFET will blow up first. So, yeah. Honestly, I'm kind of thinking that there's a good chance the VRM will straight up die on me when I try, if I try to do this. That it will just blow up. The other thing I'm kind of like thinking is that if it does run that in really low switching frequency, then there's a good chance that the VRM will actually be limiting how far the GPU core can clock, because from doing some research for the 780 Ti classified I have, I've seen a lot of people mention about that card that if you raise the VRM switching frequency, it actually clocks a lot better. So if this is running super low switching frequency, then this will clock worse, just because the transient response, as well as so basically the ability of the VRM to respond to load changes, as well as the voltage regulation, is just worse at lower switching frequencies than at higher switching frequencies. So yeah, this VRM is both not efficient enough and not this VRM is probably a pretty major bottleneck for the 780 Ti GPU core, which isn't really that surprising, because 780 Ti's are, if I'm not mistaken, either the most power hungry or the second most power hungry GPU ever when it comes to liquid nitrogen overclocking. Like, these were the first cards to be hitting over a kilowatt on their own. Like, the card on its own would pull 1,000 watts. And like there's pictures of like Kingpin running a 4 PSU setup for a 780 Ti quad SLI system, because each of the cards needed a single 1,000 watt power supply. Admittedly, in that picture they're using 1,500 watt power supply, but still, it's just absolutely ridiculously power hungry GPU the 780 Ti is, and this VRM is probably not gonna, keep up. So that's gonna be interesting. I'm like, interesting from the sense of like, well, will the card that I just revived die again? But yeah, this VRM, I mean, for air cooling, it's not efficient, but it should be fine. For water cooling, it's well, if you have a full cover water block, then really it doesn't, like, that's not going to be a problem. If you're on liquid nitrogen, then yeah, that the VRM is gonna need a lot of airflow and a heat sink probably. So we'll see. Like, I'll have a temperature probe stuck into it, and I also really want to see what kind of current draw what it hits once it's sub-zero at very high V cores. So I will have it on the current clamp. Anyway, that's the V-Core VRM. Let's move on to the memory VRM. It's a two-phase. I can't identify this chip right here. I have no idea what it is. I'm assuming this runs on 300 kilohertz switching frequency, and same 12-volt gate to source, because otherwise that VRM is going to be even less efficient than it already is. And for 1.6 volts, which is the stock voltage for the GDDR5, you're going to be looking at about 18 amps of current draw and about 2 watts of heat output on this VRM, so that's perfectly fine, because the MOSFETs are still these. Same MOSFETs, same arrangement. And since this is Hynix memory on this card, and Hynix GDDR5 does actually scale a bit with memory voltage, at 1.8 volts, you'd be probably looking at around 20 amps current draw and about 2.4 watts of VRM heat output. So that's plenty. Like, there's no problem with the memory VRM, which really isn't that surprising. GDDR5 pulls doesn't really pull that much power compared to GPU cores. So yeah, that covers the front of the card. vCore VRM unimpressive. Memory VRM is fine. I mean, I don't think I've ever seen a card where the memory VRM isn't fine. It's more been a case of like, I wish it was a two-phase or something, not really a case of like, oh, this is just bad. So yeah, anyway, let's go to the back of the card because there's some things I'd like to point out. There's these GPU hot wire points, so that's what I'm going to be using to get voltage control on this card because as far as I know, it is not... Well, I'll look into getting voltage control for some of the voltages through these. I also want to mess with the parallel vid thing. So that's both things. I'm going to be doing both of those things. Then here we have the full GPU power consumption monitoring chip. So that's the INA3221 from Texas Instruments. And the best way to trick one of these, well, the easy way is you just put a resistor across these capacitors. And typically that resistor should be somewhere between like 10 to 50 ohms. And the lower the resistance, the less power limit you're going to have, because basically how this works is that the INA3221 measures the voltage difference across that capacitor, and from that it figures out how much current is going into the card. If you put a resistor in parallel with the cap, there's going to be less there's going to be less different, like you're going to lower the difference in voltage from one side to the other, and it's going to think that there's less power going into the card. So you can raise the power limit of the card that way, and I will be doing that. Hopefully I'll figure out some way to get all of that on camera, but we all know that like when I work on modifying things, it's like I don't use a microscope because I don't need one. I can see just fine. But B is just the camera tends to get really in the way of working on anything. So yeah, I'm not sure if I'll figure out how to get this all on camera. But yeah. Also, as part of my repair for this card, these two transistors are gone. I've removed them because basically these two are used to detect the 8 pins, and due to the crack in the PCB down here, these aren't working properly. So I've removed them, and that fixes the issue with the card. So that's that. This down here, I think, are these solder pads. I think you need to solder over them to get these enabled. I'm not entirely sure. I've not fully read up on the card. But yeah, I'll cover that if I figure out how to do the volt modding, like, well, the modification video for this card, it'll be part of that. So yeah, that pretty much covers it, I think. There's nothing else really that I can think of to talk about on this card anymore. So yeah, rather unimpressive vCore VRM. Memory is fine. It should be interesting to work on this card because it looks relatively easy to work on. The one thing that I don't like is if this vCore VRM blows up on me, then replacing it is going to be a nightmare because there is no ground on this card. Like, this is ground. Like, that's a ground point. That's a ground point. That's a ground point. That's a ground point. And I think maybe there's like a strip of ground going right along there, but that's just like really awkward to get to with the memory chips being right here. So if the vCore VRM blows up, e-powering this thing is going to be a nightmare because there's just no good places to hook up the ground wires. So yeah, I really don't want to blow this VRM up until after I have all of my scores, and then, you know, then it'll be, and then I won't care so much because at least I'll have all the scores I wanted, and then I'll still try to probably resurrect the card if the VRM blows up. Obviously, I'd prefer to avoid that, but we shall see. So, yeah, that's it for the video. Thanks for watching. Like, share, subscribe, leave a comment down below or any questions or suggestions. And if you'd like to support what I do here with actually hardcore overclocking, there's a Patreon, there's shirts, there's PayPal. You can find a link to all of that down in the description below. That link also should take you to the AHOC junkyard where I get rid of hardware I don't want anymore. There's some motherboards and a 5930K listed now. And if you'd like to send in hardware to get abused and modified and whatever else, then I have a P.O. box. Send an email to buildzoid@gmail.com about, sending stuff in. Because, well, there's a limit on how old and how broken things can be for me to work on them, okay? Because I'm not going to just take everything. Especially because, like, I can't even run AGP cards. And I've had a few people say, like, hey, I want to send you AGP stuff. It's like, I don't have a motherboard to turn it on with. So, no, that's not going to happen. But things like, HD 7000 series, 6000 series, 5000 series, 4000 series, GTX 200, 400, 500, 600, 700, 900, like, I don't really care what it is. If it's if it can be if it's somewhat modern, I'm interested in overclocking it as well as modifying it. So, yeah, that's it for the video. Thanks for watching, and goodbye.